let's talk about how to figure out the number of clusters for cluster analysis, for example, k-means clustering. So let's plot some data. Doesn't matter what we use here. I think last time we said age and income. And let's plot some folks. 1, 2, 3, 4, up to 5. So what happens if we have k equals 1, so one giant cluster? With k-means clustering, we essentially would have a centroid, and all the points would belong to this one cluster. What happens if we have k equals 2? Let's draw the data again. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. So if we had k equals 2, solution might look something like this, where the center is here, and let's say this, where the center here. And let's just repeat 2 more times in this example. So let's say k equals 3. Let's say all the way to k equals, say, 6. Let's plot our data. So k equals 3, you'll probably end up with our ideal solution. And then we have our sensors. And let's say k equals 6. Maybe it'll look something like I don't know. Let's use all the colors. All right, so we have a variety of cluster numbers to choose from, all the way from 1 to 6. So how do we actually decide how many clusters we ideally want? There's something, let's plot k, which is number of clusters. And what we want to look at is the sum of a squared distance. So what's the sum of a squared distance? In the case where k is equal to 1, we have all of this distance from the center. Very, very far. So we'll get something very high all the way up here. But if we have k equals, say, 2, for example, not as far. Especially for the red ones. The red errors are very close. So summing up all of these errors, you'll definitely see a smaller error for k equals 2. And then for k equals 3, you'll have a bunch of tiny errors, which is really good. And the sum of that squared error would probably be something even smaller than 2. But on the flip side, if we're extreme and go to, say, k equals 6, again, we have all these tiny errors. But it's probably similar to the errors we saw with k equals 3. So maybe some of the errors is something like that. Let's say 4 is here, 5 is here. And what you'll notice is there's a huge drop going from 1 to 2. There's also a decent drop going from 2 to 3. But over 3, the drop in the squared errors ends up being rather small. And the ideal number of clusters is where you start to see this tapering off in terms of the square distance. So this is also called the elbow method, and we see the elbow happening around 3. This is the tapering off point.